Section 1.3 Continuity. A function f is continued at the point x equals c when the following three conditions are met. Number 1, f of c is defined. Number 2, the limit as x approaches c, f of x exists. And number 3, this limit equals the value at f of c. Now for number 2, the limit exists, we must verify that either by direct substitution, factoring, or conjugate to calculate the limit, or we make sure limit as x approaches c from the left, f of x equals the limit as x approaches c from the right. If that is the case, then the limit exists. So these are if and only if condition. Let's take a look at example 1 to try to understand what type of question you'll be asked regarding continuity. So example 1 is this function f of x equals square root of 4 minus x squared continues on the closed interval -2 to 2. So in order to verify continuity, we need to check all three conditions. So the first condition, we want to make sure f is defined on -2 to 2. In order to do so, we need to find the domain of the function. Because we have a square root and we talk about a restriction, okay, we must have 4 minus x squared to be non-negative because we cannot take square root of a negative number. Then we solve this inequality. We can factor, or we move everything to the right hand side, or multiply both sides by -1. We get x squared minus 4. Because we multiply by -1, we flip the sign, okay, less than or equals to 0. We factor, we get x plus 2, x minus 2 to be less than or equal to 0. To solve this inequality, we look at the number line. We plot the roots. Okay, the first one is -2 and the second one is 2. Now because we have a less than or equal to sign, instead of a hole, there's solid point. And we want it to be less than or equal to 0. So we can plug in, do a test point, right? Pick the number 0. So plug in 0, we get 2 times -2, which is less than or equal to 0. So it's negative in this area, positive here, and positive there. So the domain is this interval. And we write it as interval notation. Close square bracket for a solid point is -2 to 2. Okay, because the domain is -2 to 2, we will say f of x is defined on -2 to 2. If it's not defined, then we don't even need to check the rest of the condition because it will not be a continuous function. Okay, because it's defined, we need to check the limit. So we calculate limit as x approaches c, where c is any number in this interval. f of x, what is it? It is limit as x approaches c square root of 4 minus x squared. Well, because we have a polynomial and then take a square root, and because c is in between -2 to 2, 4 minus x squared is non-negative, we can take the square root, so we can pretty much plug in. Okay, so 4 minus c squared. Whatever c value is between negative 2 to 2. Well, this is exactly the function value f of c. So not only the limit exists, which is just direct substitution, but also we have the third condition, the limit equals f of c. So we can say f of x is continue on the interval negative 2 to 2. Now, why the open interval negative 2 to 2? Well, you refer back to the definition of limit. For a limit to exist, the left-sided limit must equals a right-side limit. But if we take a look at the graph of the function, okay, so it's negative 2 to 2. We do have limit as x approach 2 from the left, f of x. But x approach 2 from the right, there's no graph beyond x greater than 2. What it means is we cannot plug in a number like 2.001. So we don't have a limit on the right side. That's why it is continue on this open interval. Now, how do we discuss the endpoint? We refer to this definition, okay, one-sided continuity. Let f be a continuous function defined on the interval a comma c, close. Then f is continuous from the left at the number c if the left limit exists and is also equal to the function value. Well, what is a left limit? F of x from the left of 2. Well, look at the graph, is 0, which is the same as f of 2. Because f of 2 is also 0. You can also verify the other limit as x approach negative 2 from the right, meaning negative 1.999, f of x is also equals f of negative 2. So not only f is continue on negative 2 to 2, f is continue on the closed interval negative 2 to 2. So this is the end of the proof, and this example is also in the textbook.